Let's start by remembering that energy, E, can be written as kinetic energy plus potential energy, so 1/2 mv squared, which I'll write as momentum over 2m, plus the potential energy, U, and this is the total energy of anything. This is how we can represent energy in the classical world, but if we go into the quantum world, we have to rewrite things a little bit. So we'll start with our over 2m, that's okay. And then up here for momentum, we're going to have an I, and then an h bar, and then over here we'll have a d over dx. It's a partial derivative in the x direction. But then we're going to have to square this because we have this I here. So this becomes I squared, h bar squared, and a d squared over a dx squared. And this I squared is just going to turn into a -1. So we'll just turn that into a negative sign here. And then we've sort of rewritten this a little bit. Then from here we can go ahead and add the u, and then make this close parentheses here. This expression is called the Hamiltonian. Hamiltonian. This is an operator, and it has a little hat on top of it usually. But the operator works kind of like if you were trying to take the square root of something, right? Let's say you were trying to take the square root of this psi of xt. Well, you're not taking the square root of psi, you're taking the Hamiltonian of psi. So that means that you're trying to extract the info about kinetic energy and potential energy from this psi. And the psi naturally contains the info about, well, every piece of information that any kind of particle would contain. There's a lot of information in the psi, but the Hamiltonian is just extracting energy information from psi. Well, clearly, this is just going to equal I times h bar times the time derivative of psi. Clearly.